In section 8.5, we're going to be integrating rational functions using a method called partial fractions. And the basic idea is that given a rational function that we can't integrate using regular substitution, and which perhaps we don't have a formula for, that we can rewrite it as a sum of rational expressions we can integrate. So in this first example, we're just going to practice rewriting this rational expression using one or both of these rules. We're going to decompose the fraction, break it down into as many parts as possible using these rules. So let's go ahead and start with the fraction in part A, which is 1 over x squared plus x minus 2. Now your first step is always going to be to factor as much as possible. In part A we have some factoring to do. The trinomial x squared plus x minus 2 factors into x plus 2 times x minus 1. Now, both of these factors are linear, meaning that the highest degree term has a power of only 1. So we're going to be using the linear factor rule for part A. So according to the linear factor rule, for each factor of the form ax plus b to the quantity m, in this case, each of these is raised to the power of 1. The partial fraction decomposition is going to contain the following sum of m partial fractions. A1 over ax plus b plus a sub 2 over ax plus b squared, etc. up to the power of m. Now in this case, since each of them only has a power of 1, we're just going to have a term of one term with a denominator of the form from each factor. So we know that for some value a1, we're going to have a fraction over just the denominator x plus 2, plus we're also going to have one of the form x minus 1. Now if one of these had been raised to a second power, then we would have to continue and have two terms for that particular factor. Okay, now it makes sense that we should be able to get a common denominator and find some corresponding numerators here, some values for a1 and a2, which would give us a 1. But how can we find those? Well, to do that, we're really just going to solve a system of equations, and this is the way that we set those equations up. First of all, we're going to clear the denominator on both sides, so we're going to multiply both sides by x plus 1, or rather x plus 2 times x minus 1. Now when you do that, the denominator on the left is going to cancel, and on the right we're going to be left with a1 times x minus 1 plus a2 times x plus 2. Then we're going to distribute, and we're going to have 1 has to be equal to a1x minus a sub 1 plus a2x plus 2a2. And then we're going to combine like terms in the sense that a1x and a2x are like terms. They each have the x, whereas negative a1 and positive 2a2, these are constants which would be combined if we knew what they were. So this means that 1 is equal to a1x plus a2x minus a1 plus 2 times a2. Or factoring out the x, 1 is equal to a1 plus a2 times x plus negative a1 plus 2a2. Okay, now the reason that this is helpful is because in order to have a coefficient of x and added to some constant over here and end up with 1, the coefficient of the x would have to be 0. In other words, the x term is not written on the left, so it's 0, x plus 1 is equal to a1 plus a2x plus negative a1 plus 2a2. The only way that we could get no x is if a1 plus a2 is 0. So you take the coefficient of the x and set it equal to whatever it is, in this case 0. And then you're going to take the constants and they have to add up to 1. And that gives us our system of linear equations. Now adding these two equations together, we get that 3a2 is equal to 1 because the a1 and negative a1 cancel. Now if they didn't, we could always manipulate this multiplying by a least common multiple to get opposite coefficients and get something to cancel, or we could use substitution. In any case, this tells us that a2 has to be equal to 1/3. And now a1 plus a2 has to be equal to 0, so that means that a1 has to be negative 1/3. So what that tells us is that our original rational expression, 1 over x squared plus x minus 2, can be written as the sum of 1/3, or actually negative 1/3 over x plus 2 and 1/3 over x minus 1. And that's the partial fraction decomposition of this rational expression. Now normally we're going to be doing this because we need to evaluate an integral and we'll have another step to go. But for the purposes of this problem, we're done. Okay, on the next slide we're going to look at part B.